Hello, my name is Brian Lewis and I'm an instructor at JTNS. Today's presentation, Hazardous Atmosphere, Test, is what we're going to talk about. We're going to talk about different types of hazardous atmospheres. We're going to talk about testing, how we're going to test, why we're going to test, all kinds of things like that. Before we get started though, I'd like to take this time and just ask that you pause the video and talk about any near misses or accidents you may have had since your last JTNS visit. So go ahead and press pause, have a good discussion, hopefully a fruitful discussion. By fruitful, I mean if there has been any near misses or accidents, you come up with solutions so they don't repeat themselves. When you're finished with your discussion, go ahead and press play again. Okay, well, I hope you had a really good discussion and that it's going to be fruitful and anything that happened won't repeat itself. Hopefully no one got hurt or injured or, Lord forbid, anything worse. So one of the things that we're going to start out with is what to look for when we talk about hazardous atmospheres. So there's many different types of hazardous atmospheres, and we want to sort of break this down so we can have a good understanding of what to look for. So one type is a fuel-air mixture where we have enough fuel vapors mixed in with enough air, and then you get an explosion or some other type of fire that gets started when you have either electricity or static or a flame or something hot causes the ignition. So you're going to hear us talk about LEL, or the lower explosive limit. You might mention the upper explosive limit as well. So when it's in between lower explosive and upper explosive limit, that area in between those two, there's enough fuel and enough air to cause an explosion, a fire, etc. So that's why when we talk a little bit more in depth about the LEL, we want to avoid that situation. Another type of hazardous atmosphere that causes explosions are dust, small particles mixed in the air. When you have small dust particles, because there are so many more particles and they're smaller, you actually have a large surface area that's total area when you add all those particles up. And when they mix in the air, what happens there is it's just ripe, so that if you have some energy, like I said, electricity, whether it's AC, DC, static, or whether it's an open flame, or whether it's something that's hot that causes it to ignite, those things can cause problems. Rule of thumb, if you cannot see more than 5 foot in front of your face, then you have a potential explosive dust type atmosphere, and you need to remove yourself as quick as you can. Get out of there. Be careful. Be careful about static. Be careful about any kind of energy that would cause that to ignite. Mist or small droplets mixed in the air. These are very similar to the fuel-air mixture, and really what typically happens when we talk about these, we have a liquid that gets puts small droplets in the air, and it acts a lot like the fuel vapor mixture, except these are very small droplets of fuel. Aerosols, we're familiar with those probably. More people are familiar with those than anything else. They're potentially flammable propellants, and they're under pressure. And of course, when you impart energy onto them, it explodes. Pretty straightforward stuff. Some other kinds of hazardous atmospheres that are not explosive or flammable, we can talk about vapors. Hydrogen sulfide's one, and gases. Carbon monoxide's another one. Both those atmospheres have, as well as others, not just these two, have particular ways that they affect the body. And when you get a high enough concentration or a high enough dose, they can, in fact, kill you. That's where we get immediately dangerous to life and health, IDLH values that NIOSH publishes. So any kind of hazardous chemical that NIOSH has an IDLH for those, we need to be familiar with those, especially if we go into permit required confined spaces or we're evaluating confined spaces to see if they're permit required. Fumes is a word all of us use a lot of times incorrectly. We talk about exhaust fumes and things like that, and really what we're talking about are vapors and gases. But really what a fume is a metal oxide. And typically you get these oxides from welding, doing hot work. You get lead oxide, you get iron oxide. This is why we use inert gases around the weld, because those lead oxide and iron oxide fumes, not only do they produce very, very small fume droplets that can actually make it deep into our lungs, into our alveoli in our lungs, and pass through that barrier, the blood-lung barrier, and get into our bloodstream and create problems with things like middle fume fever. But you don't want a lot of oxygen mixing in with the weld. Obviously, it makes the weld weaker. So we want to avoid all that stuff. That's why we use the inert gases. We also have to be a little careful with inert gases, because inert gases can and will displace oxygen, and we need that oxygen to breathe. That's what keeps us alive, right? So there's a couple of different things we have to deal with when we talk about fumes, metal oxide fumes, both for the quality of work we do and the quality of health that we want, right? So where do we test for these things? Well, we want to test, as the title says, test, test, test. We want to test as often as necessary to ensure we're working in a safe environment. It doesn't always have to be a particular type of situation. If somebody is exhibiting or showing signs that they're sick or complaining about headaches or certain things going on in certain areas of the building, we need to test. We need to check and make sure everybody's going to be in a good situation. In particular, trenches more than 4 feet deep, we want to test those. We want to make sure there's enough oxygen there, no explosive atmospheres, no hydrogen sulfide, no carbon monoxide or carbon dioxide either. Carbon dioxide does not tend to be as deadly as carbon monoxide, but it still can make you sick. So we want to make sure we test for that too, especially trenches that are near the roadways and automobiles are continually pumping stuff out the tailpipes, and so we want to make sure we test and make sure none of that congregates down in the trench where we're working. Especially, if you have some kind of pump down there, some kind of generator, something that's running on gasoline, it's going to be pumping out, vapors and mist and all kinds of stuff. So we want to make sure there's not a lot of carbon monoxide there. Even if you're using a diesel-powered engine in a trench, even though a diesel is unlikely to produce large amounts of carbon monoxide, they still can produce carbon monoxide in the right conditions. So we want to test that. We want to make sure that it's okay. Propane-powered engines do the same thing. That's why we need to test around forklifts and warehouses and things like that. So not just trenches, not just confined spaces to see if it's okay to enter, but also, like I said, warehouses. We're going to find stuff everywhere. Anytime there is a question where people are either they're not feeling right, they report odd smells, report health effects, anything like that, we need to be curious and go ahead and take our monitors and test. And sometimes, basically we're all going to be somewhat familiar, even a little bit familiar, with the monitors we use to check the atmospheres before we go into confined spaces or permit required confined spaces and trenches. There are other methods that's sort of beyond the scope of this, but there's all kinds of ways to test the atmosphere. And if you need to know more about doing that, feel free to contact JTNS, your JTNS representative, instructor. We'll get back with you and do our very best to make sure we solve any mystery dealing with a hazardous atmosphere. So what do we test for? What are the tests? What do we need to look for? Well, we have a certain order we need to test in. And most monitors do this pretty well, especially those that are meant to test for confined space areas as well as trenching areas. So we first thing you always need to establish is there is the right amount of oxygen for a person to enter a confined space or enter an area. So as long as you're close to sea level, the oxygen concentration needs be between 19.5% and 23.5%. Normal atmospheric oxygen is right around 20.9%. You get below that 19.5%, it becomes difficult to breathe. And in fact, too much below it, people breathe out their last breath and they go into convulsions. It's not like holding your breath underwater. Once you get above 23.5% oxygen, what happens is materials that do not normally burn will ignite much easier, and they will burn more intensely because it's an oxygen-enriched atmosphere. So we want to be careful with that, especially if you're working with oils and greases and all kinds of stuff. If maybe you've been working on something mechanical and you've got some oil or grease on some blue jeans, t-shirt, whatever, and you go into an oxygen-rich atmosphere, it's just a bad combination. We've already talked a little bit about combustible gases and talked about the lower explosive limit and the upper explosive limit. OSHA has set values that are no-go or no entry values, and 10% of the lower explosive limit is one of those values. So when we start talking about the lower explosive limit, if you recall from just a few minutes ago, we said, hey, there's just enough fuel vapor and there's just enough air that mixed together, it will ignite and it'll explode, and that's the lower explosive limit. And what OSHA has said and established is that once you get to 10% of that lower explosive limit, you don't go in. And the reason why it's very easy to go from 10% of the lower explosive limit to actually meeting the lower explosive limit. It's very easy. It can be done very easily. It can be done very quickly in certain situations. So we need that 90% buffer there. Before we get to that limit, we want that 90% buffer because we can make up that 90% buffer really fast. And so we have to be aware of what it is and be aware that we don't want to bridge that from 10% to 100% to the lower explosive limit. Carbon monoxide, some things you need to be aware of there. In the state of Tennessee, the personal exposure limit, the PEL, is 35 parts per million. It's 50 parts per million in federal states and other states where federal OSHA is responsible for maintaining compliance. So we want to avoid that. The thing about carbon monoxide is the heme that's in our blood really likes the carbon monoxide more than it likes the oxygen molecules. And so when you get a tremendous amount of carbon monoxide in your bloodstream, your blood doesn't really want to give it up. And so it's very important that we recognize that headaches, nausea, and all the things that are associated with carbon monoxide exposure rarely abate themselves or disappear just as soon as you go to fresh air. It usually takes a little while. So we want to be real careful with carbon monoxide. I know that typically we think about carbon monoxide when we smell the byproducts of either a diesel engine or gasoline or a propane engine or something along those lines. But real carbon monoxide does not have taste, it does not have a smell associated with it. But what we end up doing as people, we end up smelling the byproducts of a gasoline, propane, diesel engine or something along those lines, and we associate that smell with carbon monoxide. And that's perfectly normal to make that association. But do realize you don't have to smell anything to be overexposed to carbon monoxide. Hydrogen sulfide is very interesting. It can be just lethal. Typically, it's a rotten egg kind of smell. In general industry, you have a limit of 20 parts per million. You have of any time, never go over 20 parts per million, 50 part per million maximum, 100 part per million, immediately dangerous to life and health, and 10 parts per million for construction. And most of the time we use the construction 10 parts per million when we're evaluating a permit required confined space or a trench. It is the most conservative number. I do not play around with that number. In fact, I would tell you if you've got anything much more than one or two, you ought to be asking yourself a question. We're going to talk a little bit more about these numbers, not in great detail, but just a little bit more. And it's just human nature that when you're given a number as a limit, that, hey, as long as it's below that number, typically, it's safe and we don't think much about it. But if a number surprises you, whether it's above the limit or not, you need to ask questions. We need to ask questions. We don't need to be on automatic and just make assumptions. That's going to get us hurt or killed, and we want to avoid that, right? We want to avoid that. So where do we test for this stuff? Where do we test for it? And there's several areas we want to make these tests as far as places. But when we talk about a person, we want to test in the breathing zone. If somebody's going down into a manhole or into a particular space that's got an odd configuration, we want to test where the person's going to be breathing. And typically, especially in trenches, you don't always get to work standing up, right? A lot of times you're down working on your hands and your knees. And so we want to test where the person's going to be breathing. Just don't test at the top or the bottom or the midsection. You got to test everywhere that person's going to be. And you want to test in the breathing zone. Now, a breathing zone is just a fancy word or a fancy phrase, really, for an imaginary hemisphere around a person's nose or mouth. And typically it's 6 to 9 inches from shoulder to shoulder, where a person can turn their head to the right or the left. And in that 6 to 9 inches in front of their mouth into their shoulders is going to be considered their breathing zone. So we want to test in the area where the person is going to be standing, squatting, kneeling, where they will enter the space as they go down a ladder or up a ladder. And we want to test in particular where we think their face is going to be, where their mouth and nose is going to be. And if you're actually wearing a monitor, as you should be, because we should be monitoring continuously, you want it as close on your shirt as you can get it to that imaginary 6 to 9 inch hemisphere going around a person's nose or mouth. And that's very important that we do this accurately as we can, because that's where they are going to be. So what kind of monitoring do we want to do? Well, you want to get, obviously, before you go into a trench that you suspect or that's near an area where you can pretty well assume there might be something in it, you want to test before you go in. You want to test continuously. When we're dealing with a permit required confined space, we want to test before you go in, and we want to test continuously because conditions arise from time to time. We want to be aware of them. And if you remember from permit required confined space training, anytime the attendant notices anything that's a danger to the entrant, they ask the entrant to come out. The entrant comes out. Anytime the entrant hears an alarm go off on their monitor, they stop what they're doing. They leave the space. So whether it's a trench, whether it's a permit required confined space, we want to test before you go in where a person's going to be working. We want to test continuously around their breathing zone while they're working. And if any kind of dangerous situation arises, we want to leave. Now, not everything is going to be a permit required confined space. Not everything is going to be a trench. There may be warehousing operations or something else where a lot of propane powered forklifts are being run. And if you've got that and they're not maintained well, you're going to have a lot of carbon monoxide. Don't forget that there are spaces other than what we think of as dangerous that we need to test and we need to be aware of. Anytime you're in a space that doesn't have natural ventilation or the mechanical ventilation fails, you can have an accumulation of vapors, gas, mist, dust. All that stuff's important that we need to pay attention to. Here's just an example of a particular type of monitor, and as you can see, it's got percent of oxygen and the lower explosive limit, carbon monoxide, and hydrogen sulfide. And typically we get digital readouts. So that's a really good thing. That's something that we need to be aware of. We need to have familiarity with whatever the monitor you're using to make sure that you know how to operate it and you know when it's operating correctly. So keep that in mind. Some other things we need to talk about when we talk about these monitors, because a lot of times we just look at numbers for numbers' sake, and unless you think about what those numbers represent, you're doing yourself a disservice, okay? So it's really important that these portable gas monitors are calibrated as often as the manufacturer requires them to be tested. Sometimes the manufacturer will require that a portable gas monitor is sent off and calibrated there. Sometimes they send sensors or cells, and the cells are already calibrated, and you replace the old cells. Sometimes you can, if you're certified, you can do the calibration yourself, or locally someone might be trained and certified to do the calibration correctly. And typically it's at intervals of yearly, every 3 years or something like that. What matters is that you do it as often as the manufacturer requires it. I also encourage people to do field calibration and testing. So a lot of times you can obtain gases that are a known quantity, and you can hook up your portable gas monitor with those gases, and the container that's got the gas in it will tell you how many parts per million of oxygen it is, tell you how many parts per million carbon monoxide, hydrogen sulfide, etc. And if your portable gas monitor doesn't give you that reading, you know something's wrong. I also encourage people to test them when you're out at the site. Before you start testing the air that's inside a trench or permit required confined space or anything else, take them outside where you know the air is fresh. Take them where there's not any traffic, and make sure that the actual monitor is working correctly. If all you care about is putting the numbers down on a sheet of paper and not trying to figure out if that machine's giving you good information, there's potential there for somebody to get hurt or worse. So take every opportunity to make sure your equipment is in good shape. And that's not just, say, a harness and a lanyard or anything else that you think about when you think about permit required confined space. That includes the monitor. Do not just be satisfied to put a number on a piece of paper. That's a bad way to think about this. Make sure that monitor is working correctly. Make sure that it's intrinsically safe. I know a lot of times people toss these monitors around somewhat carelessly, but if there is an explosive atmosphere down there and the casing of your monitor's been beat up and you take it down into the space with you, well, it may be the spark that blows you up. So intrinsically safe is something we have to worry about with anything electronic. That power circuit can be the spark if the conditions are just right to ignite a hazardous atmosphere. So we want to make sure that any monitor we take with us for continuous monitoring is intrinsically safe. We want to make sure that any monitor that we use to determine the atmosphere before we enter that particular space is intrinsically safe also. I encourage you not to take anything electronic down there that you don't know if it's intrinsically safe. Sometimes you got to take walkie-talkies, two-way radios, stuff like that. Make sure all that equipment's intrinsically safe before you go into a space. As a reminder, what I've been trying to pass along is please be diligent in maintaining your equipment. Please be diligent. Just don't be writing numbers down on a piece of paper to satisfy a safety requirement. Think a little bit about the numbers. Think a little bit about your machine, about your portable gas monitor. Make sure it works right. Make sure you test it. Make sure you can trust it. Make sure it's received its calibration from the manufacturer like it's supposed to. If you're going to do a field calibration, make sure you do that right. Make sure you test it in fresh air and that it doesn't give you crazy readings. Make sure it works properly. And don't make guesses. We want to remove as much risk as possible, and we will take guesswork out of it. Absolutely take all the guesswork out of it that we can. So please be aware of that. And don't forget, if we're diligent, if we're not guessing about what's going on, not guessing what the air smells like, all this other stuff, we're going to test, and test. And remember, it's not always going to be a confined space. It's not always going to be a trench. It could be a warehouse type situation or any other kind of situation. We want to make sure that we don't ignore certain atmospheres just because they're not a trench or a confined space. Things can happen. We want to be careful with all that. I appreciate your time and your attention. If you have anything to add or any questions that you want answered, please contact your JTNS instructor. We may not know the answer, and if we don't, we'll research it and get back to you. But if we do, we're going to try and get back to you as quick as you can. Once again, thank you for your time and attention. Have a great day. Be safe. Thank you.